Welcome to week 1 of sound synthesis. This week, we will be setting the foundations for our look into synthesis. We will start by discussing the basics of sound and how we can describe it. This will provide us with the tools we need to talk about shaping sound and creating new sounds. We will then discuss the components that are common to many of the synths we will be looking at throughout the course. We will also be taking a look at the early history of synthesizers from the start of the 20th century up to the development of modular synthesizers. Lastly, we will have a look at Reactor, get an overview of the entire program, and also build our first basic synth. In this lesson, we will be looking at ways of describing sound. What is sound? How do we talk about the differences in loudness, duration, or even what separates the sound of a violin from a guitar? Technically, sound can be described as a vibration through a medium. This means that sound can travel through air, water, or anything that can propagate waves of energy. Sound can also be described through several key properties. Think of a plucked guitar string. When we release the string, it begins to move away from us until it reaches a maximum, at which point it comes back towards us, almost reaching its original position. This cycle is repeated again and again at the same rate or period. The number of these periods in 1 second is known as the frequency. Frequency is measured in hertz, so 1 hertz is a single period in 1 second. A single back and forth, which is a very slow frequency. Using these ideas, we can accurately describe how many times a second a sound is vibrating the air around us. Frequency can also tell us about the length of a wave. Sound has a speed at which it travels through materials. In air, sound propagates at 1,138 feet per second. This means that a 1 hertz wave will travel 1,138 feet in a single period. This also means that a room would need to be that large in order to accommodate a full cycle of that frequency. This is often why small rooms can have a very poor bass response. Another critical property is pitch. While frequency enables us to describe the rate at which a sound is vibrating, as humans we are generally more interested in the ordering of frequencies from low to high. We describe this ordering of frequencies as pitch, with a high pitch corresponding to a high frequency and a low pitch corresponding to a low frequency. When talking about pitch, we are also interested in the relationship between sounds. If we hear a frequency of 440 Hz in isolation, then we're not likely to recognize that as an A on the keyboard. However, if you first play a sound of 440 Hz and then play a second sound at 880 Hz, we will hear that as a specific relationship known as an octave. The two pitches are played at the same time, we perceive the relationship between the two. For example, when the frequencies have a 2-to-1 relationship or a doubling, we say that they are an octave apart. When they have a relationship of, say, 5-to-4, then we say they are a major third apart. This means that we are perceptually interested in things like the doubling or halving of frequencies rather than a fixed number of frequencies in between the interval. For example, let's hear what an octave actually sounds like. So if we start at a frequency of 220 Hz, or a low A, the octave above that would be 440 Hz, which is also an A. And an octave above that again would be 880 Hz, which again is also an A. We can also hear what a major third sounds like, which is a 5-to-4 relationship. We can hear this by playing a C and an E on the keyboard. Up next, we're going to talk about amplitude. This term is used to describe the magnitude of the sound in reference to the height of the waveform. In Reactor, this will generally refer to a wave that fluctuates between -1 and 1. The amplitude affects the perceived loudness of a sound. Loudness is similar to pitch. If pitch is the way we perceive frequency, then loudness is the way we perceive amplitude. Loudness is how we describe the ordering of sound intensity from low to high. Just like pitch, loudness is subjective. What is too loud for one person may be comfortable for someone else. Loudness is also similar to pitch in that we are sensitive to logarithmic changes rather than linear changes in amplitude. For example, 2 people clapping doesn't feel twice as loud as 1 person. And 100 people clapping certainly doesn't sound 100 times as loud. If it worked that way, then we would all go deaf every time a large group of people started clapping. For synthesis, we are mostly interested in how loudness changes over time. Which brings us to duration, which is how we order sounds from short to long. Distinguishing between short and long sounds plays a role in how we perceive rhythm. Taking loudness and duration together, we can describe the envelope of a sound, or how the loudness changes over time. We can describe these changes in loudness as different stages. The initial ramp up in loudness is called the attack phase. This can be thought of as part of the sound that you created when you strike or pluck something. The ramp down after the peak loudness is known as the decay. This can be thought of as a sound decaying away after the initial burst of energy. This decay stage can stop at a sustained level and hold the note out as long as the note is being held on the instrument. This stage is set to a loudness value between 0 and 1, unlike the other stages which are set as a length of time. The final stage is the release stage, and represents the time it takes for a sound to fade to silence after the note is released. Let's look at some of the envelopes from various acoustic instruments and see how these loudness curves define the sound. Looking at a snare, we can see how the envelope quickly jumps up and then rapidly decays off. This is what gives the snare that quick burst of sound at the very beginning. Whereas if we look at the envelope of something like a violin that's being slowly bowed, we will see a gradual increase in volume and then a gradual decay off. The envelope is one part that defines a sound. The other aspect is all of the frequencies that make up each sound. With the exception of a perfect sine wave, sounds that we hear are made up of multiple frequencies. The lowest frequency in a harmonic sound is known as the fundamental, and is what we normally define as the pitch of the note. In a pitch sound, the sounds above the fundamental are known as overtones, which are also called harmonics. Harmonics are integer multiples of the fundamental, and are found in waveforms such as sawtooths, square waves, triangle waves, trumpet tones, human vowels, and any other sound that gives us a strong sense of pitch. Partials are sine waves, but can be inharmonic, meaning that they are not integer multiples of any fundamental. Inharmonic partials tend to make sounds more metallic. Putting together both the envelope of a sound and its harmonic content provides us with a way to describe the fingerprint of a sound. This is known as the timbre of a sound. Timbre is the synthesis of all of these features previously described in this section. Timbre is the way we describe how one sound is different than another, and is typically what we mean when we are talking about the color of different sounds. Timbre is what allows us to distinguish one type of instrument from another, and is what we're talking about when we say sound is dark, bright, sharp, or dull. The art of synthesis is really all about shaping sound, using all of these features to create new and interesting timbres.